Guys, this video is going to look at the Walding Chapter 2 in-text questions from question 11 onwards. Looks like these ones are delving into acceleration. So question 11 reads, plot an ST graph and a VT graph of the data of a bowl rolling down an incline listed in the table below. So let's start off with a bit of vocab first. So ST graph, that's telling us our vertical and horizontal axis. The horizontal axis is given second, the vertical axis is given first. So it should look something, well, that would be displacement, that would be time. If, however, you forget that, one thing to always remember is that unless it's really important to help with extracting, say, a gradient or an error or something from the data that you're going to then manipulate, you should always be plotting time on the x-axis, because if we think about all these rates that we're dealing with motion, velocity equaling displacement over time, and acceleration equaling velocity over change in velocity over time, the over time is indicating time should be on our x-axis there whenever we plot it. And so, well, a VT graph is going to obviously look with velocity on the y-axis and time on the x-axis. So let's have a look. We've got 5 seconds, 0, 1, 2, 3, 4, 5, and we're going up to eventually displacement of 75 meters. I'm not going to be able to put, so 20, 40, 60, 80. Alright, so at 0 at 0, at time equals 1, displacement is practically 0. At 2 it was 12 seconds. At 3 it was 27 seconds. At 4 it was 48, so let's see, that was 40, that was 60, so 48 is going to be there. And then finally at 5 was 75, so it's going to be there. And what we see, I mean, my crappy drawing aside, it's that curving up type thing. Well, that kind of goes straight and straight, but hey, hopefully your picture's better than mine at home. Same thing for velocity time. Let's see, we're going to go up to 5 seconds. 1, 2, 3, 4, 5, and we're going up to 30 in this case, so let's do that in, say, 5, 10, 15, 20, 25, 30. So let's see, first time is 0, at 1 second it was 6, so just above that, at 2 seconds it was 12, so just a bit further, 18, halfway, 24, almost to the, and then all over the top, and this one's a lot easier to draw, because it should be a straight line. Something to notice is that whenever there's acceleration, a VT graph will be straight, while an ST graph will be curved. That's a really important thing to remember. Okay, and we want to, by inspection of the data, state the acceleration of the rolling ball. So let's see, what's our definition of acceleration? Acceleration equals change in velocity over change in time. So that means it's going to be able to come from our VT graph. The gradient of our VT graph, that equals m. M's a symbol for gradient. It's something to do with the French, I believe. M of VT graph. Okay, but we can just get this number from the data, the numbers from the data as well. So let's use the total change in velocity, because it should be straight, and if we look at it, we can see it goes up by 6 every time, so it's definitely straight. So it's going to be 30 divided by 5, which equals 6 meters per second. Acceleration is change in velocity per change in time. If every second it goes up 6, that means it must be 6 meters per second squared, not meters per second. Alright. Question 12. Okay, another one of these table type books. In this case, we are just filling it in based off the definition. I'll do the first couple, and then you guys can work out the rest of the answers are in the back, remember? So we're using the formula A equals delta V over T as our definition of velocity, or V minus U over T. Remember, we use U for initial velocity. So let's have a look at that first one. We've got V, U, and T. So delta V equals 8, because we are starting at 10 at U, going up to 18. So that's a positive increase. We have the T equals 2, so acceleration will equal 8 over 2 equals 4 meters per second squared. Looking at our next one, we have a delta V of 4, and we're ending at 42, so U is going to equal 42 take away 4 equals 38 meters per second. Actually, what I'll do, I'll just do this one a little bit more formally for us. Delta V equals V take away U. So if delta V in this case equals 4, equals 42 take away U, and we can rearrange that, add U to the other side, subtract 4, we get that U equals 42 take away 4 equals 38 meters per second. We know that acceleration equals 4, delta V equals 4, so if A equals V over T, or delta V over T, T is going to equal delta V over A equals 4 over 4 equals 1 second. And I will not going to bother with, yeah, all the rest are just further applications of what we've just done there. Calculate the delta, work out the acceleration, or E is a little bit different, using A and T to work out the delta and then use the delta to work back, but I have faith you can do that. I don't think you want me to sit here and waste time on these. Okay, highest road tested acceleration reported for a car is 0 to 96.5 k per hour, which is 26.8 meters per second. In 3.98 seconds, blah. Calculate the acceleration. So let's identify what we have. We have 0 to 26.8, so U equals 0, V equals 26.8 meters per second, and we know that the time equals 3.98 seconds, and we are asked to work out acceleration. Now, for these sort of things, we can assume acceleration is constant. It is not going to be speeding up at one rate, and then as it gets a little bit faster, it starts speeding up even more. Though that is more like a real life situation, but we have to assume acceleration is constant. So again, we're just going to use the formula from before. Acceleration equals delta V over T. In this case, will equal 26.8 take away 0 over 3.98. 26.8 divided by 3.98 equals 6.7 meters per second squared. Okay, 14. Highest speed by a rocket engine wheeled land vehicle was 290 meters per second. Its acceleration was measured at 4.2 meters per second. How many seconds would it have taken to reach the speed? And it says from rest. So again, U will equal 0, V will equal 290. T is unknown. Acceleration equals 4.2 meters per second squared. As A equals delta V over T. T equals delta V over A equals 290 take 0 over 4.2 equals 69 seconds. Okay, question 15. The head of a rattlesnake can accelerate at 50 meters per second when striking a victim. If a car could do as well, how long would it take for it to reach a speed of 27 meters per second from rest? So let's say V equals 27, U equals 0 because that's coming from rest. Acceleration equals 50, T equals unknown. Same formula as before. T equals delta V over A equals 27 take 0 over 50. Should be just over a half, 0.54 seconds. 16. A muon, which is an elementary particle, and it's an electric field with a speed of 5 times 10 to the 6 meters per second, whereupon the field causes it to decelerate at 1.25 times 10 to the 14 meters per second. How much time elapses before it stops? Now this is important where you get your directions right. I'm going to purposely stuff up my directions first, and we'll see a couple of different combinations. We'll see we'll get the time will be always the right size, but sometimes we'll get a negative. So let's identify u correctly. So u equals 5 times 10 to the 6, and v equals 0. It wants to go to 0. But we're going to say that a equals 1.25 times 10 to the 14. Now the fact this says decelerate should tell us it's negative, but let's say that we mess it up. So t equals delta v over a equals 0. Take 5 times 10 to the 6 divided by 1.25 times 10 to the 14. Now do be careful with your powers of 10. Make sure that your calculator is actually attaching the power of 10 to that number. So for example, if you did 5 times 10 to the 6 and then took the negative of it and then you divided it by 1.25 and then you put on the n times 10 to the 14, it can very easily do, oh yeah, that divided by that and then multiply it by that. So we can see that's 10 to the 6, that's 10 to the 14. We should get a very small number here. If we don't get a small number, so I don't care about the negative, I'm talking about the size, then your powers have been messed up somewhere. In which case, use your brackets a bit better. We get that this would equal negative 4 times 10 to the negative 8 seconds. But we can't have negative time, which tells us we've done a sign incorrectly. And this is because of this deceleration. This is negative. Okay, which means that has to be negative, which means that will become positive. Okay, do be careful with things like that. I mean, you can recognize and go, oh yeah, okay, it should be negative. But I'm still going to be looking at you working out. If you left that positive and left that positive, I don't care if you correct that. That tells me that you're not actually paying attention to what the language is asking you. So do be careful with that. You have to get your directions right. With simple things like this, not so much of a drama because you'll still get the right magnitude and maybe you can interpret it. But if you're doing more complicated problems, you really want to make sure that your direction is correct. Okay, question 17. Now we're looking at instantaneous velocity. So from figure 2.12b, which is to the left of it, calculate the instantaneous velocity at 4 seconds. Calculate the average velocity over the whole 5 seconds. Okay. So the instantaneous velocity, we need the gradient of the displacement time graph. So we've got a displacement time graph there. We need to work out the gradient, and we want the gradient at 4 seconds, which means our tangent line for that curve must hit at 4 seconds. So I'm going to try to roughly draw this. It starts at negative, so 1, 2, 3, 4, 5, negative 10, negative 20, 10, 20, 30. Looks like it starts here at negative 20, curves up to cross at 4. And then goes way up from there really quick. Okay, so when we're talking about taking a tangent line, I want a line that is going to cross that's okay. Why did that move down? Okay, it's not ideal, but you get the kind of idea. And here we want to get the rise and run of this. Now, this is really hard to do on this because the obviously I'm just trying to draw a picture by hand. What I would recommend you do is get a ruler, put it over there, and I mean you can do it in pencil, don't tell anyone I said that, but you can use a pencil, make a couple of marks, and then read your change in y, your position over your change in time, your y, your x, change in y over your change in x. So I'm going to sort of guesstimate it based looking on the picture here, and I reckon that one of the points it's going to go through is going to be 10, 5, and the other point it's going to go through let's do 3, negative 10, sorry, negative 10, 3. So remember, that's our y, that's our x, that's our y, that's our x. So we want change in y over change in x is going to equal our m, which equals our velocity. So change in y, that's going to equal 10 take away negative 10, and it wouldn't matter which one we did, and I'll show that in a second, over 5 take away 3. That's the important thing to get right. And we would end up there with 20 over 2 equals 10 meters per second. If we'd gone the other way and gone negative 10 take away 10 over 3 take away 5, we would have got negative 20 over negative 2, which, sorry, negative 20 over negative 2, which also equals 10 meters per second. So it doesn't matter which point you use, but you've got to make sure that you're consistent. Now, let's have a look at the answer. The answer for 17A, when I can find it, there it is, 17A is approximately 13 meters per second. Now, that's not too bad guessing by eye, so I don't know, maybe I should have gone a bit high, a bit steeper on that. With that sort of question on an exam, you're never going to get it perfectly right. Now, 13, 10 might have been a little bit too low for my tangent, so I probably would have given my point for doing the right method, but my tangent was kind of sucky. If you were within, say, a couple of percentage of that, you'd be fine. Okay, it's just knowing the method for it. Let's look at B, and B here is asking for the average velocity, which is a lot easier to do. So we just need to look at the displacement values, and I'm going to use the start and the finish, because that's really what displacement's asking about. It starts at negative 20, so let's go for change in S equals minus negative 20, and it ends at 30. So that's going to equal 50. And the time for that will equal 5 seconds, which means that velocity equals 50 over 5 equals 10 meters per second, which is what the textbook gives us. That one's a lot easier to do because we just need the start value and the end value for our displacement, which will also give us the start value and the end value for our time as well. Okay, question 18. For the motion of the bungee jumper shown in figure 2.15, which is above, there we go, calculate a whole bunch of things. Okay. Firstly, calculate the displacement and distance travelled after 40 seconds. So we have here a velocity time graph. So we're going to need to work out the displacement for a whole bunch of different sections here. Now, when we're looking at a velocity time graph, the displacement is going to be the area under the curve. By what I mean, the area under the curve is the area between the line there that we have marked on it to show the velocity over time and the x-axis, and you can have negative area. So our graph kind of looks like this, where it goes up and down, about a bit steeper than before, and then back up. So this area here, A is going to be positive, but B will be negative, okay, because it's a negative velocity for our dimensions of our triangle. So you've got to be careful with that. So let's work out the area of A. The area of A is going to be triangle, half base times height. The base is from 0 to 30, so it's going to be, and the height is from 0 to 10, which equals 150 meters. The fact that the velocity is negative really doesn't matter. Okay, yeah, it's coming back, but all we care about is what's the area of that whole shape. So the velocity is originally going away, stops, comes back, keeps coming back. So the velocity has been increased to 10, then starts to reduce, then starts to increase, positive again. Ends up going negative as well, where it starts coming backwards. So even though the velocity or the acceleration is negative, it's still going forwards in this section here. So yeah, it's speeding up, then it starts to slow down, so even though it's slowing down, it's not actually going backwards. Here it's starting to go backwards. go backwards, so that's still going to be a positive area. The area of B, triangle again, the base is from 30 to 50, so it's going to be 20, and the height is from 0 to negative 10, so times negative 10 equals negative 100 meters. So now we want to work out the displacement. The displacement is going to equal 150 plus minus 100 equals 50 meters. So after that time, it's travelled 50 meters down. And think about a bungee jumper. Yeah, they jump off, they don't come all the way back up to the top. The distance, though, is going to equal the 150 down plus the 100 meters back up equals 250 meters. That's a really good type of question. Okay, B. Calculate the acceleration at 10 seconds, 30 seconds, and 45 seconds. So we're looking for the instantaneous acceleration. We're not asking for the average, otherwise it would have said the average acceleration. We want to know what is the acceleration at those points. So 10 and 30 aren't going to be too troublesome to do. Hang on, I've got different displacement here. Let me double check that. 30 times 10 would be 300, half. Yeah. 30 times 50. 20 times 10, 200, 100. I'll have to look at the errata for that. I am 90% certain of that. I will put a comment in down below if I find a different answer for that. However, oh, they want after 40 seconds. That's where I went wrong. Sorry, so if I read the question right, travelled after 40 seconds. So this second bit here, that is wrong. So I only need half of that because the triangle is the same both sides. It's going to be a base of 10, vertical of 10, so that's going to be 10 there instead. 10 times 10 is negative 100. Half of that is going to be negative 50. Which means that now we have take away 50 equals 100 meters, and then that's going to be plus 50 equals 200 meters. Yeah, because they work out the total just above. Okay, calculate the acceleration at these points in time. So 10 seconds, we can see it's somewhere on that line, and we can see at that point it has gone from 0 to 10 in a time of 10 seconds, so that should be a acceleration at 10 will equal 10 over 10 should equal 1 meters per second. Okay, it's gone up by 5 over 10 is half. Doesn't get to 10 till 20. Equals a half, 0.5 meters per second. 0.5 meters per second squared. Okay, the next one we want to look at 30 seconds. So if we look around 30 seconds, it's a straight line from the time equals 20 down to time equals 40. So I'm going to use those. Acceleration of 30 equals, if it's negative 10, so that's going to be negative 20 divided by 20 equals negative 1 meters per second squared, and the acceleration of 45, same kind of thing, it's in that line from 40 up to 50, so that's a time of 10, and it goes from negative 10 up to 0, so that would be an increase of 10 equals 1 meter per second squared, which I'll just double check quickly. Yes, that's correct. C, sketch the acceleration time graph. Well, we've just worked out the accelerations there, so the acceleration time graph would, if that's 1 and that's negative 1, oops, positive 1, negative 1, for the first 20 seconds, so 10, 20, 30, 40, 50. So for the first 20 seconds, 0.5 because it was constant. At the next 20 seconds it was -1, and then the next one it was +1. You can see how this graph is broken. Do not connect the lines. D. When was he stationary? So stationary would be when velocity is 0. Okay, if he's stationary, it means velocity must be 0. So if we have a look at that, that would be at t equals 0, t equals 30, and t equals 50. A. When was his acceleration constant, but not 0? That looks to be all of it, because his velocity is always a straight line. It is never horizontal. Okay, acceleration constant. Yeah, so that looks to be the whole thing. I'll just do a quick one. Where is it? Yeah, we're looking at E now, aren't we? Now, the thing is, one problem I have with this is that at time equals 20 and time equals 40, there's a spike. That means his acceleration is changing at that point, and it looks to be an instantaneous change. So the way I would answer this is that for t equal to 0 and less than 20, not equal to, because at 20 he's doing something weird, and for t between 20 and 40, and for time above 40, that's when it's constant to me. At those points, 20 and 40, it's doing something stupid, but not too much to worry about. At F, when was his velocity constant but not 0? Well, we just said before he was stationary at 0, 30 and 50, which means his velocity should be constant at those points. And at 20, even though his acceleration is weird, his velocity is still constant at those points. Where is it? Question 18 we're doing, aren't we? Where was his velocity constant but not 0? Oh, constant, sorry. Nowhere. Because his velocity never stays the same, it's always changing. So I hope that makes sense. So from there we can see that his velocity is always changing. On to the next question. 19. The graph to the left shown in figure 2.16 illustrates the motion of a skateboard rider, again velocity time graph. Calculate his displacement after 1 minute. Calculate how far he travelled in the minute. So same as before, we're going to be doing some areas. Unfortunately this time we don't have nice simple areas. You have to work out each one individually. So I will show you a couple for these. So goes up and not as up, and then back down to 0, and then a little bit across a little bit. This is velocity, this is time. That was at 10, 20, 30, 40, 50, yep, and 60. Sorry, that sizing's off a bit there. Now, this one's a triangle, this one's like a parallelogram, this one's a triangle, triangle, rectangle, triangle. This you can either remember the parallelogram rules, which I really wouldn't expect. You can, I mean, hopefully you can do it, but if you don't, it's not a drama. But you could also do this as a triangle on top of a rectangle and do that. So I'm going to give them names A, B, C, D, E, F. Now D, E and F are going to be negative. Be aware of that. Area of A equals half base times height. Base is 10, so half times 10. The base is always going to be 10 for at least for these. And the height here was also 10 according to the graph. Equals positive 50 meters. Area of B. Now we can use the parallelogram rule. Parallelogram rule is where you go half the height. In this case the height is from this side to this side across the parallelogram, and then you add the two, the long and the long and the short side together. So half base A plus B. I will have a double check that. A parallelogram. Sorry, that's a trapezium, not a parallelogram. So yeah, add the two sides, divide by 2, multiply by the height. So we have here on our picture, we have our two sides 10 plus 15 times the height, which is going to be 10 over 2, equals, let's see, 10 over 2 is 5. 10 plus 15 is 25, 25 is 125 meters. You could work out a square then a triangle on top, which is probably easier if you're not remembering your geometry off the top. So I hope you can recognize that shape. C, same triangles, another triangle, times 15 times 10 equals 75 meters. Now if we get to area D, E, and F, area D is a very small triangle. In this case, it's going to be half times -5 because it's going below, times 10 equals -25 meters. Area of E equals a square of -5 times 10, so it's going to be -50 meters. And area of F is the same shape as the other one of area D, so it's also going to be another -25 meters. So the total displacement is adding up all these things. So we've got 50, 100, so that's going to be 200, 250. Take that away, takes us back to 200, equals 150 meters. B wants us to work out the distance. Okay, so again in this case we're just not going to worry about these negatives. So that was 200, 250, 300, 350. C, what is it? C. At what stage was the magnitude of his acceleration the gradient? So we're looking for the steepest line here. Now the two little triangles down D and F are not going to be the steepest, and neither is B. We can see that they're just going to be a change of 5 over 10, and so the magnitude will be quite small. We've got 2 there, we've got 1, and for A that is 10 over 10, so it'll be 1. And we've got 1 there that's 15 over 10, which would be 1.5. So it would be when acceleration equals -1.5 meters per second squared in that box we called C before. Or when t equals 20 to 30. When was he stationary? So we want when was velocity 0. So at t equals 0, t equals 30, and t equals 60, he was stationary. When was his acceleration negative and constant whenever the line went down? So that would be from t equals 20 to 30. And from 30 to 40. Note, I didn't go 20 to 40 because it wasn't constant during 20 to 40. There were two different constant accelerations. So that's important to note. When was his velocity constant, but not 0? Well, let's have a look. His velocity is only horizontal between 40 and 50. T equals 40 to 50. Okay. Olympic equestrian 3-day eventing is held over 4 days. First 2 days consist of dressage, 4th days for show jumping, 3rd day speed and endurance. Okay, so we care about that. So we're talking about 3 different stages of horse riding apparently. We've got the trot, then the fast steeplechase, we've got some time and velocities. Stage 3 is another trot exactly the same. Or stage 4, 10-minute rest, then stage 4 is a testing 14-minute cross-country gallop, 34 can't draw a VT graph of the motion. Okay, so it's going to be like what we did before, and then we want to calculate the total distance covered in this travel in the event. So let's draw a VT graph. So if we look at our velocities, we've got a 13, a 41, another 13, and then 34. So let's go 10, 20, 30, 40, 50. And let's see, it takes 10. First one takes 10 minutes, then 5 minutes, then 10 minutes, then 10 minutes, then 14 minutes. So let's see, 10 plus 5 is 15, add another 10 is 25, add another 10 up to 35, then add another 14 would give us close to 50 minutes. So let's do 50 minutes. 10, 20, 30, 40, 50. 10, 30, 50, 10, 30, 50. Okay. So, first bit was 13 kilometers an hour for 10 minutes, so that's going to be about there. We are drawing VT graph. Yes. Then we go to the next bit, which is 5 minutes at 41 kilometers an hour. So that's going to go halfway into that, and then it comes back down to here. Does another 10 minutes at that, and then it did 10. That was 30. That would have been 25 to 35. Yep. So a 10-minute rest, and then it did at 34 kilometers an hour up here, about the 4 thing. So in this case, it's because there are all these constant velocities. It wasn't the velocity was changing, it's just that it was this constant velocity for different times. So we end up with this broken graph here. We want to work out the area. We can work out the area under the curve on it. It's just going to be, all these little rectangles. But you may as well just use your velocity time equation. We've got all these minutes, and we've got, actually we can't even use the area, sorry, cannot use the area because this is in kilometers per hour and that's in minutes. Kilometers per hour, they are different units, so we're going to have to convert, aren't we? So let's do, stage 1, we had 13 k per hour equals 3.6 meters per second. And we had a time of equaling 10 minutes, which is 60 seconds. Let's look at our equation. Displacement is going to equal velocity times time. I hope you can see how I rearranged that. So the displacement, or the distance, while we've got velocity, does want distance, so distance equals speed times time. So distance equals 3.6 times 60 equals 216 meters. For stage 2, we had the 41 kilometers per hour, 41 k per hour, which is 11.4. Time equals 5 minutes, which would be 3. Why did I do 60? That should be 600. Yep, 2160 meters. Don't know what I was thinking there. 11.4 times 300. Distance is going to equal 4 times 300 equals 3,420 meters. Stage 3 was the same thing as before, so that's just going to equal distance equals 2160 meters. Stage 4, distance will equal 0 meters because there is 0 velocity. Stage 5 was 34 kilometers per hour. It was 9.4 meters per second. Time equals 840 seconds. So distance equals 9.4 times 840 equals 7,896 meters. So the total distance is going to be the sum of all that, plus 160, plus 260, plus 3420, gives us a total distance of 15,636 meters. Alright, the next section in the textbook looks to be constant motion equations, so we're now using slightly different ones from before, so I think that's a good time to finish off this video. Thanks guys.